Welcome back to another explainer. Today, we've got something absolutely fascinating for those of you who geek out over how things are made, optimized, and managed on a massive scale. We are taking a deep dive into the 2025 Anna University curriculum for the Bachelor of Engineering in Industrial Engineering and Management. Honestly, I like to think of this specific curriculum as the ultimate blueprint. It's literally designed to take a student starting from a total blank slate and step by step build them into a strategic decision maker capable of revolutionizing modern manufacturing and enterprise operations. Let's get into it.
Okay, let's briefly look at our agenda for today. We'll start with the industrial engineering roadmap, then move on to building the scientific foundation, followed by mastering modern engineering tools. After that, we'll look at advancing to systems design, and finally wrap up with specialization and industry readiness.
All right, Section 1, the Industrial Engineering Roadmap. We are grounding our entire analysis today directly in the official 2025 regulations from Anna University. And, what stands out right off the bat is how incredibly balanced this curriculum is. It isn't just about crunching numbers in a vacuum. It meticulously blends basic sciences like math and physics, core engineering sciences, and, crucially, vital humanities courses. This three-pillared approach ensures students develop not just technical prowess, but also the communication and management skills that are absolutely essential for real-world leadership. So the crucial point here is understanding the ultimate destination of this degree. The program clearly defines three program-specific outcomes, or PSOs. Think of these as the core DNA of the graduate. PSO 1 is all about mathematical modeling, optimization, and statistical methods, basically making data-driven decisions. PSO 2 focuses on mastering modern engineering tools and software for process improvement. And PSO 3? That's all about research aptitude, teamwork, and ethical practices for lifelong learning. Every single class, lab, and project you'll see over the next 4 years is meticulously designed to hit these three specific goals. Now, to make this massive 8-semester journey a bit easier to digest, we can chunk it into 4 logical phases. Phase 1 spans semesters 1 and 2, which is all about building that rock-solid foundation. Phase 2 covers semesters 3 and 4, where the focus shifts entirely toward integrated systems. Phase 3, taking up semesters 5 through 7, is where things dive incredibly deep into specialization. And finally, Phase 4 is semester 8, which is pretty much dedicated entirely to immersive project work. Moving right along to Section 2, building the scientific foundation. Looking closely at the first 2 semesters, we see a really brilliant contrast designed to create a completely well-rounded student. On one hand, you've got the rigorous theoretical sciences, applied calculus, physics, chemistry. These are the heavy hitters that give students the deep analytical tools to understand complex physical systems. But right alongside them, you have crucial skill development courses. We're talking life skills, English essentials, and a really grounding cultural perspective through courses like Heritage of Tamils. This parallel track guarantees the student isn't just technically capable, but culturally aware, emotionally intelligent, and ready to actually communicate their ideas. Let's jump to Section 3, mastering modern engineering tools. And this brilliantly illustrates how the curriculum immediately targets those program outcomes we discussed earlier. Look at this lineup. First, computer programming with Python, where students are getting their hands dirty with data structures and libraries like NumPy and Pandas. Those are absolutely essential for modern data analysis. Then there's engineering drawing, focusing heavily on 2D and 3D object creation using modern CAD software, plus a course called Re-Engineering for Innovation that deals directly with prototyping and reverse engineering. These are not abstract textbook concepts. These are the exact modern software tools required to drive real industrial process improvement. But hey, the tools they master aren't exclusively digital. Semester 1 actually includes an incredible hands-on course simply called Makerspace. Just look at this practical progression. Students start by completely disassembling and assembling common household appliances to see exactly what makes them tick. Then they move to actual welding practices like gas metal arc welding. From there, they tackle electrical wiring and circuit boards, and finally, physical fabrication using 3D printers. It totally proves the curriculum's dedication to real-world practical applications. You don't just sit at a computer and design a system. You actually learn how to physically build the thing. All right, Section 4, advancing to systems design. As we enter semesters 3 and 4, the coursework rapidly elevates the student from basic tool wielding to full-blown system analysis. They dive into the kinematics and dynamics of machines, figuring out exactly how mechanical parts interact. They explore fluid mechanics and machinery. But notice how it's perfectly blended with modern tech. They are simultaneously taking applied data science and a dedicated course in systems design and ergonomics. They are no longer just looking at a single gear or a single line of Python code. They are designing complete, integrated systems where mechanical parts, data streams, and human operators all have to interact seamlessly. Finally, Section 5, Specialization and Industry Readiness. The shift in focus here is very deliberate. By the time students hit semesters 5 and 6, the core coursework pivots almost entirely toward optimizing industrial operations at a massive, macro level. We are talking deep dives into operations research, quality design and control, and supply chain management. They are learning how to look at complex, multi-million-dollar enterprise operations, identify those hidden bottlenecks, and use mathematical modeling to streamline processes, dramatically improve quality, and slash overarching costs. Now, what's really interesting about this specialization phase is the sheer variety of the elective streams. As they customize their degrees, students can choose courses like Big Data Analytics, Industrial IoT, Circular Economy, Machine Learning, Lean Manufacturing, and Industrial Robotics. These are not legacy topics. These are the exact cutting-edge skills that drive massive future demand. This is precisely how the curriculum prepares students for those high-paying, specialized modern industry roles. It maps perfectly to where the global job market is heading right now. And then you hit semester 8. Notice something missing? There are no traditional theory classes listed here. The entire semester is completely dedicated to project work or an internship come project work. It commands a massive 16 periods a week and is worth 8 full credits. This is where the whole 8-semester journey culminates. The student must step out of the traditional classroom and test all their accumulated skills, from Python and CAD to supply chain management, in a demanding, real-world industrial environment. When we look back at the entire blueprint of this degree, it's so fitting to return to program-specific outcome 3. The curriculum aims to have students demonstrate research aptitude, teamwork, ethical practices for continuous self-learning and professional growth throughout their careers. Because look, while knowing Python and data analytics is vital today, technology is going to change. The true enduring value of this degree is creating a highly adaptable, lifelong learner who knows how to collaborate and solve the unforeseen engineering problems of tomorrow. Which brings us to the end of our roadmap and leaves us with one final inspiring thought. Armed with an incredible foundation of theoretical science, hands-on mechanical skills, data science capabilities, and macro-level supply chain mastery, how will you apply these tools to revolutionize real-world industrial operations? Thank you so much for joining me on this explainer. Keep learning, keep optimizing, and we will see you next time.